Thank you. We have Antonio visiting from Italy. I'm going to mispronounce the university, so I'm going to let you say it, right?
Yeah, University of L'Aquila.
L'Aquila?
L'Aquila, yes.
That's where he's from. And he's in the mathematics department. And I'm just thrilled to have him talk about his different method of doing, I guess it's a little old. It's been around a while, but you've developed, really kind of pushed it with some fast methods and explored where it can be used in practical signals. So,
yeah. So now you're spoiling my presentation.
Yeah, I'll just shut up and I'll sit down and let you talk.
Okay, thanks a lot, Frank. Thanks for having me here. Thanks to the organizers.
Thank you from Professor David Anderson that presented and introduced Professor Antonio from Italy. And now we are going to proceed to his presentation. Thank you very much.
Okay, thanks a lot. It's really formal. I didn't know. Okay, so
Yeah.
I tried to be really formal. By the way, thanks really a lot. It's really a pleasure to be here. Thanks you for having me here. And so the talk I'm going to give you is an overview of the research activity I started here at Georgia Tech when I was a postdoc. And so we will restart from scratch. So the idea is to introduce the problem and then go through a review, a historical review of what has been doing, or what has been done in the literature, and then I will walk you through where I started working on this research direction and the last advancements and the open question that we have. So it all starts with a signal, right? A measurement. I mean, you should know, right? But in this presentation, I'm going to focus on 1D signals. Okay, and even though keep in mind that most of the research we have can be extended to higher dimensional or to multivariate, so multi-channel signals. And what we want to do is extract time frequency information from these signals, or to understand what are the hidden features. Okay, and of course, I mean, you have many applications wherever you can measure some quantity over time, or even over space sometimes. The problem is that in real life, you have no stationarities, and these create a lot of troubles to classical techniques, Wavelet, Fourier, or techniques derived from them. Okay, so let's give an example. Let's start from a differential equation, which is simple, and for which we know the ground truth. So with this differential equation is a Duffing equation, can be reformulated by simply collecting the x variable here in a way that now we can imagine this part to be a stiffness coefficient, which is varying with position. Now, this may look a little bit weird, but I mean, it's a simple system. You can imagine it to be like a mass connecting with a spring, and then you have a forcing term, which is oscillatory, which is applied to the mass. Now, to add a little bit spiciness, we allow the coefficient corresponding to the spring to vary with the position. Okay, so it's a nonlinear system now. Okay, and we can solve it once we fix the parameters. And how we can use any numerical scheme, just the classical ones, the vanilla version, and we can find a solution. Now here I'm plotting for a set of parameters, the x and x prime. Okay. Now what we can do is we can take the x prime to be our signal, and we want to study it. We want to see the frequency contained in it and what are the hidden information. Now, naked eyes, we immediately see that we should have two frequencies, right? Active. One in low frequency and one in high frequency on top of it. Okay. Let's try to apply standard classical techniques like short time Fourier transform. Okay. If we do it, so we apply the spectrogram, that's the kind of plot we get. And here you see that we have a low frequency, a middle frequency, and high frequency, and possibly even higher frequency, which is a little bit counterintuitive because we expect it to have two components, right? We can try continuous wavelet, and the answer we get is pretty similar. So we still have these three components, and the fourth one is no more even visible. Okay. You probably are aware, but people in the wavelet community have been developing better techniques with respect to continuous wavelets to try to improve the time frequency representation. And in particular, Ingrid Debashy and her colleagues developed what is called the synchro squeezing approach, which is basically starting from continuous wavelet or spectrogram, and you shrink information in the vertical, with respect to vertical axis, so you focus information in frequency domain, okay? If we apply it here, that synchro squeezing, we get these three components, which are way more sharp, and so the image is crisper, but we still have three components, okay? Okay, and this is clearly not what we would expect by naked eye inspection. So what's going on? Now, the idea that a researcher called Hilbert-Huang had like 20 years ago now, it was to approach this problem in a different way. So instead of first trying to produce directly time frequency representation, his idea was, let's first decompose this signal into simple oscillatory components, okay? And so his idea was what we can call in Latin, divide et impera approach, which means split and conquer, okay? So we split the signal and then we conquer component by component the frequency. What is the idea is to split that signal in simple oscillatory components. What do we mean by that? What is a simple oscillatory component? Huang and collaborators propose an informal definition that they call intrinsic mode function, IMF. And the idea is to basically generalize what a sinusoidal curve is. So you want to have extrema, maxima, minima, and with the same number of zero crossing, which, if you want, translates into all the maxima are positive and all the minima have to be negative. Okay, and then you want the signal, so the function, to be symmetric with respect to the horizontal axis, which means you take an envelope connecting the maxima, an envelope connecting the minima. These two envelopes have to be symmetric. Okay, an example of these functions, there could be a sinusoidal curve, and with amplitude modulation and frequency modulation over time. Okay, or it could be sinusoidal but with no smoothness. Okay, all these functions are reasonable. I mean, they're good IMFs for the definition we gave. Now, the next question is, I mean, this is great, this is cool, but how we produce this decomposition? And over the last 20 years, researchers have produced several techniques, many techniques. And we can summarize them into two groups. Techniques based on optimization, where you basically predefine a basis and you use that basis to represent in a sparse way your signal, okay? And you have like empirical wavelets, sparse time frequency representation, you have many other techniques. Their limitation is that you need to a priori select the right basis and you have to optimize to find the best way to represent it on the basis. And then there is the other group, which is techniques based on iteration. And among them, there is the pioneering empirical mode decomposition, which is the method proposed originally by Huang and collaborators. And after that, other techniques, which are variation on empirical mode decomposition, have been proposed, because that technique dates back to 1998. The other alternative iterative method is what is called iterative filtering, which is the technique developed here at Georgia Tech, at the School of Mathematics. And that's where I started working on this field, because I met the researcher that developed the method, and I helped them further developing it and analyzing it mathematically and accelerating it. So what we're going to do now is we review what empirical mode decomposition is all about, for those of you that do not know it, and then we will go into the iterative filtering. What we want to know is that these techniques, they do not require an a priori choice of a basis. The problem with empirical mode decomposition is that its convergence is not known. We are going to review this concept. And the stability is a problem, but that part has been fixed with subsequent methods. And for iterative filtering is a completely different story. We have convergence and stability, as you will see. Okay, so let's talk about Hilbert-Huang Transform. What is Hilbert-Huang Transform? Basically, is the full package that, given a signal, does the decomposition and frequency analysis. We call it this way because they call it that way. And Huang is for the decomposition part, and Hilbert is for the frequency analysis, as we're going to see. So let's start from empirical mode decomposition, so the decomposition part. I just let you observe this number, which is the number of citation of that original paper on Scopus. So that's not Google Scholar. Okay, if you check Scholar, it's way higher. Okay, and that's the little number, the number of citation of the first author. How many citations the guy received? Consider that now is going like more than 3,000 citations per year. It's adding, but the trend is like increasing linearly. So you know the number of citations is keep on increasing in a crazy way. So how it works, the technique? It's a really simple method, but it's even simpler if we see through an example. So we take a non-stationary signal and we want to decompose it into simple oscillatory components. Okay. Now, naked eyes, you can see that there is a trend, there is a high frequency oscillation, and on top of a low frequency oscillation, right? Or middle frequency. Why we can see the high frequency oscillation? Because we can imagine that there is this kind of moving average on top of which you have the high frequency oscillation. So that's exactly how EMD works. It tries to approximate this moving average and then use it to subtract it from the signal. And what is left is the high frequency oscillation. Okay, plain and simple. So, but how to compute this moving average? The idea by one is that of using envelopes connecting the extrema. We take an envelope connecting the maximum and then an envelope connecting the minima, and we take then the average curve between the two. And that's our approximate moving average. Now, why approximate? Because keep in mind that we know exactly, or up to numerical precision, where the extrema are located, but we have no idea how to connect them. Okay. And so, as you can imagine, there are infinitely many possibilities of how to connect this extreme. So the red curve is, known up to infinitely many possible variations. Okay. So, but what we do is we take the red curve and we subtract it, and that's what we get. So we get what is left in the signal and the moving average we just computed. Okay. If we re-add these two together, we will reproduce the original signal. Now, as we said, this curve was just approximate. So the idea is to apply an iterative scheme on this signal here. We treat it as a signal, so we reapply the same procedure, we recompute the new moving average. And if this moving average now is small enough, let's say in norm 2, then we stop and we declare that what we have is an IMF, or we keep on subtracting. So, and once we are done, that's an IMF, and now we can move to the remainder and we reapply the procedure from scratch, like if it were a brand new signal. Okay, so then we identify the new moving average, we subtract it, and so, and then we check again iteratively if the moving average is 0. And once we are done, and we stop as soon as the remaining part of the signal does not contain any more oscillation. And then we can go back and compare with the ground truth, and we see that there is a really good matching. Some issues are present on the boundary. We're going to review in a moment, but the method is working really nicely. Once we get this decomposition, what you can do is the Hilbert part. So we take now the IMF, which now here I call like F function, and I compute its Hilbert transform. Why? Because if I now take the IMF plus I as imaginary number times the Hilbert transform, this is a new function, which is a complex function, which has the nice property to be an analytic function, which means we can rewrite it in polar coordinates, and the angle is rotating in a way that is always increasing. Okay, so then we can compute its derivative, the derivative of the angle, and that can be defined as a frequency because it's always possible. Okay, so that's what they define as instantaneous frequency. Okay, I mean, they do not define it, they simply took it from the literature because Hilbert transform was out there in the market for many, many decades. But the brilliant idea is to combine Hilbert transform with the idea of decomposing, because Hilbert transform works magically because this is a simple rotation around the origin of the Gaussian plane, but that because the IMF is a simple monocomponent. Okay. Okay, so let's see how it works. So let's go back to this signal, and we saw the synchro squeezing, which was the best way to represent the time frequency content of it using, top techniques in the literature. Now what we do is we decompose first. So we apply this different approach. We decompose first the signal into IMFs, and that's what we get here. Yeah. So, and now you get, as expected, two components, okay? What you expected by naked eyes checking. And now, for each of them, we do the Hilbert transform, and we get the instantaneous frequency. We put together the two curves, and that's the plot that you get. And now you see that we have a low frequency oscillation and a average frequency, which is extremely non-stationary, okay? And this explains a lot of things. Okay. Now, the first idea that it could come to your mind is, oh, okay, this is working, but because we first decompose. What if I decompose first and then apply synchro squeezing, for instance, or any other technique? Is it going to work better? Let's try. So that synchro squeezing of the full signal is Hilbert transform after decomposing, right? Now let's apply synchro squeezing to the first IMF and Hilbert transform to the first IMF. That's what you get. Here you have this highly stationary component, time frequency. This is what we get with synchro squeezing. So even if you decompose first, wavelets, synchro squeezing, short time Fourier transform, they're going to still produce this behavior. The reason is simple. The basis, so all these techniques, they use predetermined bases which cannot capture the strong local non-stationarity that you have in this specific signal. And so they instead produce a projection on their basis, which in this case looks like that. So is a mathematical artifact coming from the technique. So it's not physical. It's physical if you use a certain basis, let's say, okay? So it's just a projection. If you take the second IMF, they do match as expected. This is just a low frequency component, which is not changing too quickly in frequency. Okay, so now all this said, it looks like the Hilbert-Huang transform is a perfect package. You have it, you can use it, and it solves all your problems. So, it was great. Nice talking with you. We can go home, right? I mean, I can enjoy pizza at this point. Sorry, guys. So, we have a lot of pizza also for you, but we're going to eat it for you, no worries. Anyway, so no. Why? Because there are a lot of other problems. First of all, stability. What I mean by stability in this context? So let's take an example. We take these two signals that are pretty similar to each other, one in black, one in red. They're really close. Red here is constantly above in the first half and then constantly below in the second half. If I run empirical mode decomposition to decompose it, that's the decompositions I get, okay? And if we focus our attention on the trend, you see immediately that the red curve is not going as expected. It goes below the black in the middle, whereas we expect it to be above in the first half and below in the second half. So this behavior is completely off. This is what in the literature is referred as instability. It's slightly more complicated than instability, but we can accept that definition. Okay, so it's not working. It's not doing what it should do. It basically is influenced by small perturbations. Okay, so it's kind of instability. But this problem has been fixed in what they call ensemble or noise-assisted empirical mode decomposition. How they do it? They basically take the original signal and then they produce an ensemble out of it. How? They add noise, hundreds of different realizations of white noise, and then they produce hundreds of new signals, and then they decompose all of them, and then they take an average decomposition out of it. It works. I mean, it does stabilize the problem, but there are two issues. First of all, is that you have to have a big number of perturbation to make sure that the noise you inject cancel, because those are random but independent realizations. So to have a perfect cancellation, you have to have hundreds of them. The second small issue is that it's really, really slow. Empirical mode decomposition was fairly fast, but this is extremely slow. I mean, it takes hundreds of times more to do the same decomposition. As a matter of fact, no one used these techniques. Everyone in application keeps on using just the classical EMD, and they do not care about instability. There is another tiny problem, which is called convergence. Now, every time I give a talk, I tend to recall what convergence is all about. Okay, I mean, we know, we learn it, but what does it mean in practice? Okay, so I always give this example because at least for me, it makes things way cleaner or simpler to understand. So we all know accurate and precise. What does that mean? So stability and convergence are the very same concept, just with different names. So here we have an example of what the ideal method we want to have should be. So it should be stable and convergent. Okay. Here is an example of a method which is stable but not convergent. And here is an example of non-stable but convergent. And here is non-stable and non-convergent. So stabilizing means that you don't have any more of these problems, but you could have one of these two scenarios. It could be non-convergent but stable, and convergent and stable. So in the literature, no one could prove so far any kind of convergency of EMD and its alternative versions. So the technique we are, or many people are using nowadays, can shoot at random positions, okay? And nobody can ever discover it unless someone shows you the target. And in real life, you don't have the target. So you're just shooting in the dark, okay? So that's why it's better not to use empirical mode decomposition from my humble point of view, at least not at this stage. And the other little problem is that if you try to extend to higher dimension these techniques, the computational times becomes even higher because you have to build envelopes in higher dimensions. So for all these reasons, in 2009, Lin, Wang, and Zhou from the School of Mathematics here, they propose an alternative technique called iterative filtering. The idea is to simply redo the moving average calculation in a more mathematical fashion. How? Using integration. Okay. Now, why we want to use integration? It's really intuitive once you define. So S is your signal, and you define W to be a filter. Now, but in this context, more than a filter, you can imagine it as a weighting function. So what we are doing is the following. We fix X, the position in the signal, and then we take weights that are centered at that position X, and we basically compute, think about this as a summation, a weighted summation of the value of the signal around that point. So what we're doing is a weighted sum, which computes the local average. How to get it is the filter, the W, the weighting function, you choose it in a way that is going to be compactly supported, like this function here or these functions here. So it's going to be 0 outside an interval, and then it's going to give a lot of importance to points at the center. Okay, if you do that, you're going to compute the local average. Okay, but the nice part is that this formula can also be viewed as a convolution of the signal with the filter, which is the weighting function. Okay, and this makes a lot easy to do a mathematical analysis of the algorithm. As a matter of fact, first of all, I pointed out integral are linear operators, as they say in mathematics, which means it's a linear function. Okay, but the method is nonlinear because even though the integral is linear, the interval in which we are integrating, which is the support of this function, so the non-zero interval of W, is defined based on the data itself. So think about this L as L of S. So then this function here is a nonlinear function now, okay? And that's what makes the method nonlinear. Okay, so what we were able to prove back when I was here at postdoc was the convergence of this method, okay? And we were not only able to guarantee convergence, but we also provide an explicit formula which tells you what an IMF is going to be if you choose a specific filter. And this formula, or at least the hypothesis, allows you also to guarantee convergence a priori if you choose the W function, so the filter, in a special way. The special way, it's simply you can choose any shape you want, but once you choose it, you convolve that shape with itself. And now that new filter is going to guarantee you the convergence. That comes magically from the mathematics, okay? Because this basically guarantees that the Fourier transform of the filter has positive Fourier coefficients, okay? Okay, but that was back in 2014. And here you can see application. I mean, that's the signal I showed you earlier. You get the same similar nice decomposition. You can apply to even no smooth signals and you can decompose them. Or if you take a stationary signal, like super simple, with two components, if you add noise and even more noise, you can reconstruct the two components plus a bunch of noise, okay? So it's stable as expected. And you can apply to real life signals like super non-stationary, it's like tsunami arriving, I mean, on the coastline of Hawaii. Or the example I showed you earlier, now you see that the trend is as we expected. So the red curve is above here and below afterward. Or here is another example, which is basically, we took the magnetic field of the Earth measured from satellites, and the satellite, we would love to just measure the Earth magnetic field, but the satellite is measuring the magnetic field in the upper atmosphere, which contains contribution from the Earth, but contribution also from the sun and from, deep space. So what we did is we decompose that signal into IMFs, and then we studied them statistically, and we discovered that there was a quite big difference between the low frequency IMF and high frequency IMF. So we split them into two groups. We added together the low frequency IMF, and we compare the summation of the low frequency IMF with the outcome of a model that has been developed in the last 50 years in geophysics called Chaos 6. I mean, now it's version 6. This model that has been developed by several groups of researchers around the world allows you to estimate the Earth magnetic field with high accuracy. So we compare our outcome with the model estimation, and we got an error of 10 to the minus 6. So, but we just push a button and we just did statistical analysis on the IMF. So we didn't know anything about, we didn't put any condition of what was the magnetic field, what are the features. We didn't have to train any model. And this model requires every year to be recomputed because the magnetic field is evolving every year. So it's pretty powerful, the approach we have. Now, more recently, we first of all proved that the composition you can get is finite. So you don't have it, you cannot have infinitely many IMFs. And but more importantly, we studied the boundary effects. So then the problem with EMD is that you do not have convergence guarantee, so you cannot even study how much the boundary can influence your decomposition. So with iterative filtering, instead you can do it. We were able to derive a simple formula. I mean, it looks ugly, but it's really simple, which allows you to estimate, given a certain IMF, and you know how many iterations you're going to apply, it tells you how much the error propagates inside your decomposition due to certain errors at the boundaries. And then we also propose recently a naive approach to handle better the boundary, which is basically pre-extending your signal. So if you do not want to lose any data point, you can pre-extend left and right, and then you make the new extended signal to be periodical. If you do it, like here in this example, green is the original data that you do not want to lose, and you pre-extend it in red, and in any way you want, and then you do in blue, you make it periodical by basically windowing it. Okay, and you can use this kind of extension on any technique, wavelet, empirical mode decomposition, or iterative filtering itself. And here I show you a small example, but I want to show you here a real life application. So basically, we found this paper on Scientific Records published a few years ago, where they were applying empirical mode decomposition to the signal you see here, which is a signal representing earthquakes with their magnitude, daily earthquakes with magnitude from 5 up to 9, the magnitude, I'm missing now the word, but anyway, so that magnitude. And they run the decomposition with EMD. Now, the decomposition contains many IMFs, but then at a certain point, you see that there are like strange waves appearing nearby the boundaries. And the more you go to low frequency, the more these waves propagates inside the signal. Okay. And if you look at this detail, I'm not sure how much you can read, but these values here, you can read -20, 20. So the oscillation at this IMF goes from -20 to 20. And the original signal was from 6 to 8. So that oscillation does not come from the signal, clearly. Those are boundary errors that are propagating inside the signal. Okay. So you can easily fix this problem by using the pre-extension I showed you earlier. And you can get a super clean decomposition where all these IMFs basically disappear. Okay. Okay, but the really important result we got was the acceleration of the algorithm. What we realized is that if you do convolution in a discrete setting, you are basically using a matrix vector multiplication, okay? Where your matrix, which represents the convolution matrix, is a matrix with a special structure called circulant or triplets, more in general. And these matrices have a real special feature. You can diagonalize them using the Fourier basis. So what we discovered is that the formula we had originally, which was the convolution, it can be calculated super fast using the Fourier basis. So what we do is we do the FFT of the signal, the FFT of the filter, and now we can simply do a vector multiplication. So we multiply to vector, and what we get is the solution. Plus, the other interesting result is that now this formula can give you the opportunity to have a direct method, because if I know a priori how many iterations I need, I just plug it in this number here, and I compute in one shot the result. So the IMF is given by that formula, where n, you can choose it a priori. Okay, so the method can be accelerated even further. Now, keep in mind, FFT is extremely efficient. So we were able to speed up 100 times the classical iterative filtering, which was roughly the same speed as EMD. With the extreme nice property that now EMD was not stable, you need to stabilize it at the cost of, as you remember, introducing a lot of noise. And so that will require like perturbation of the signal. So EMD is not stable, but the variation of EMD, they are hundreds of times lower than EMD. So fast iterative filtering is 10 to the 4, 10 to the 5 times faster than the stable version of EMD. And so we are talking about hours with stable version of EMD versus seconds with fast iterative filtering. Okay, so extremely powerful. And all thanks to the mathematics. Now, I want to just point out, because they usually ask me, So are you just doing Fourier transform of the signal? So you do the FFT of the signal, and that's it, right? Say, no, I mean, the FFT here is not used to really filter out your IMFs. It's a tool that we use to do the calculation of the convolution. So the irony is that we were developing a method that could solve the limitation of Fourier transform. And now we discover that through Fourier transform, used in a super wise way, we can do extremely cool things. So the Fourier transform is used, but just as a tool to speed up the calculation. But if you think about, it's all based on the Fourier transform of the signal, which means if you can somehow imagine what is this part here, which is kind of weighting each Fourier transform coefficient of the signal, then you can do exactly what iterative filtering is doing. So it's kind of really using the Fourier transform in a super weird way that only mathematics can give you. So it's, for me, it's fascinating. You know, I'm a mathematician after all. Anyway, so more that we discovered recently, we have a paper on arXiv. So we discover that one of the big problems with an EMD, I mean, besides stability and convergence, is that you cannot preserve energy because the IMFs are known to be non-orthogonal, which means you have the L2, so the energy of the signal, you take the L2, so the energy of the IMFs, the summation of the energy of the IMF does not match the energy of the original signal. Why? Because of this non-orthogonality of the IMFs. That's a big problem because you cannot guarantee that the IMFs you are producing are meaningful from a physical point of view. But with iterative filtering, we were able to prove that if you work in the frequency domain, you are basically preserving the energy in Fourier domain. So we have a theorem that tells you, I mean, it's pretty simple, but that the energy of the signal in frequency domain is conserved using the IMF produced with iterative filtering. So you can guarantee that the IMF you have, they are non-orthogonal, but their energy is the same as in the original signal. Okay. I just briefly mentioned here, we extended this method to higher dimensions, trivially. So now the algorithm can work with data of any dimension. And we've also extended to multivariate, so multi-channel. Now, with multi-channel, let me give you an example here to clarify. So imagine you have two channels here, black and red, and you want to decompose them. You can always run decomposition in parallel where the two channels decompose, but then since these techniques are data adaptive, the IMF you're going to produce, they're going to contain different frequency. So the first IMF in red and the first IMF in black, they don't have the same frequency, okay? And similarly, the second IMF, okay? And the third is just the trend. Why? Because the two channels contain different range of frequencies. With multivariate, what we do is, in a simple way, we synchronize the choice of the filter for all channels. And then we decompose the first channel using this unified filter to discover that the highest frequency is only in the red channel, not in the black one. And for the second, you see that you should see that the two frequencies are just the same. They're just a phase shift. The third frequency is contained just in the black channel, and then the trend is contained in both of them. So this allows you to create decomposition that talk each other. So the first IMFs, they contain the same range of frequency, as well the second and third. Okay. Now, you may think that it's simple because you take the two channels, you take the highest frequency among the two channels or the N channels, and you use that as a reference for your filter. But this is not quite right. So in the literature for empirical mode decomposition, what they develop is called multivariate EMD. And what they discover is that if you do the naive way, so you take every channel and you choose the highest frequency among all of them, and you build your filter out of it, it may fail. So then what because basically different channels are kind of projections of a higher dimensional signal which is kind of rotating in an n-dimensional space, where n is the number of channels. And these projections, they may hide the actual highest frequency. So what they are doing is reprojecting the signal n times, or at least n times, to guarantee, and for each of them, they check what is the highest frequency, to guarantee that the filter is really capturing the highest frequency. So we do not need to do this reprojection, which is time consuming. We do it directly working in the n-dimensional space, where n is the number of channels. And we look at this n-dimensional signal as a single signal that is rotating and changing over time. And we look to the oscillation of that object, and we use it as a reference to fix the dimension of the filter. And this works magically well. Okay, so what is next? So far, we talked about the decomposition part. Even the Hilbert transform has limitations. I'm going to show you in a moment. So for this reason, we try to develop a new technique, fast, robust, that allows us to extract time frequency information from the decomposition. The idea comes from the observation that once you have a decomposition, once you have the decomposition, the IMFs are clean and simple enough that you do not need a machinery like Hilbert transform to extract the frequency and energy. So we have this ugly formula that is put there just to scare mathematicians, but the concept is extremely simple. And that I'm not going to usually say to mathematicians, or I say, oh, no, that's too trivial. It cannot work. So, but the idea is extremely simple. Once you get the IMF, so I'm going to go back to that in a moment. Once you get the decomposition position, I touched the wrong channel, the wrong cable. Yeah, now it's good. Now it's just on the wall. It got to catch on the wall. I'm moving too much. Yeah, no, just a second, Yeah, you have to have faith in it. Okay, so once you get the decomposition here into IMFs, now if you look at this IMF, that the projector is nicely undersampling, you see, or you should see, let's see the second, which is slightly more clear. If I ask you what is the frequency in this signal, you can, naked eyes, you can say, oh, okay, here I see that there is a lower frequency, then it gets higher, higher, and then get lower, lower, higher, right? Why? Because you see at the oscillation and you check the zero crossing. So that's exactly what we're doing in the IMFogram. So we make the strong assumption that the IMF is stationary inside one oscillation, or actually half of oscillation. So we assume that from this zero crossing to the subsequent one, this curve is perfectly sinusoidal, which is not true, okay? But, we make this assumption. We are mathematicians, so we can do these kind of things.
That's what engineers do.
Okay, but, also mathematician, because the problem it would be too complicated. So we assume that the stationary is just a sinusoidal curve, and say we count the zero crossing, and we say, okay, in between zero crossing, frequency is not changing. And then what we do is we need the curve. So we interpolate. So we compute for each zero crossing the relative distance between two subsequent zero crossing, and then we connect these values with the linear interpolation. So from here we get the curve which represents instantaneous frequency. What about the energy? Similar story. I mean, here you see that the energy is going up and down, down, up, because you see the amplitudes. So what we do is we take the absolute value of each IMF, so we flip the down part here. Then we connect all the maxima of this absolute value and we linearly interpolate them. And that's an instantaneous amplitude curve. Okay. Now, with these two information, you can build directly the IMFogram. But the IMFogram is going to contain a lot of fine details, plus there could be some small oscillation because of rounding off, like the zero here, zero crossing. We are not really computing the exact one. We are computing the sample point closer to zero, which can be a rough approximation. So what we do is we window the instantaneous curves we built, instantaneous frequency, instantaneous amplitude, And the window data, that's what we're plotting here. Somehow is what you do with short time Fourier transform, right? You window. But the windowing we are doing is not on the original data, but on this instantaneous frequency and instantaneous amplitude plots. So the windowing is not going to be, so the size of the window does have to be really extremely careful chosen, right? Anyway, so that's the plot we get, which is extremely similar to what we got originally with if you remember, with empirical, so with one transform, this plot here, this one here, right? With the difference that this takes for like 10,000 points, it takes like 15 seconds to produce. For us, it's just 1 second. So it's way faster. But it's not only a matter of being faster, which is something I should also do, right? Speeding up a little because the time is running. So anyway, we got an infogram which is pretty similar to Hilbert transform, but it's even better than that. Let's see a real life signal. Here, we're taking electron density. That's a collaboration I have with a research group of geophysicists. They have, they're working with ESA. We have data from the satellites, and we simply measure quantity regarding, the magnetic field of the Earth. And we try to do short time Fourier transform, continuous wavelet, and then we try synchro squeezing, and then we try Hilbert transform. And looks how ugly it gets. There are all these lobes that are clearly mathematical artifacts. So the formula are simple and they are like neat, but the numbers you get, they are not as good as you wanted. That's what you can get with IMFogram, which is really close to synchro squeezing transform, but it's way more local and way crisper image. Okay. So altogether with IMFogram and fast iterative filtering, we have a super fast and super robust approach for time frequency analysis of signals. So again, we're done, right? It was great. So can I add pizza? No. So there are a lot of more slides, but I'm gonna go really quickly, like 5 minutes, right? Is it good if I take for 5 more minutes?
Yeah.
Okay. So let's just have a glimpse to what is the future, okay? Or at least it's the past for me, but it's the future for the research in application. So all these techniques, fast iterative filtering, ensemble empirical mode decomposition, and any other stable approaches for iteratively decomposing a signal, they have a big problem. Let's consider these two components as IMFs. They are non-stationary components with a varying frequency. I choose them wisely. Their instantaneous frequency curves look like this. So each instant of time, they're well separated, but if I look overall, the ranges of frequency are overlapping. This means that if I try to apply any technique developed so far, iterative technique, we cannot separate these two as we would like. So let's combine these two components in a signal and let's feed it into fast iterative filtering. And that's what you get as a decomposition. So what's going on here? The algorithm is doing its job and is doing it nicely. So it's convergent, it's stable, it's doing everything. So this is meaningful from a physical and mathematical point of view, but it's not the way you would like to see it. What's going on? Let's go back here. So iterative filtering is all about, in some way, as a bandpass filter with a fixed bandwidth of frequency. So you fix the highest frequency and you capture whatever is in that bandwidth somehow. So you're gonna have this part and that part, and in the middle, nothing, which is exactly what you have here. Then you lower and try to capture this frequency, which is contained in all these parts. And that's exactly what you have here. And the more you go down, so in practice, if you connect all these parts here and all these parts here, you can reconstruct the two components you wanted. So they're there, they're just cut in a weird way somehow. And all techniques you have out in the market, iterative techniques, that's what they give you. So the idea we had when I was here as a postdoc was to develop an alternative version to iterative filtering, which we call ALIVE, which is adaptive local iterative filtering. But the true reason is because it took ALIVE to prove that it was working. Okay, so what we were doing is simply, instead of doing a convolution now, we allow the interval of integration to vary from one point to the next one. Now, it's really simple, the formulation. I mean, it's just really the same formula as before. You just allow the filter, the weighting function to change, to adapt point by point its size. Okay, it's really simple. Mathematically, guys, it's a nightmare. So it works beautifully. We can let the data to give you how the support of the filter should be. You apply it, it works nicely. I mean, not perfectly, but really nicely, right? But mathematically, guys, it's a nightmare. So we spent like 4 years trying to prove its convergence without any success. We involved super experts in what is called generalized locally tablets theory, which is a super advanced linear algebra theory developed to generalize tablets theory to try to guarantee convergence. All we could get at the end was this conjecture that maybe it's going to work, but we couldn't prove anything in practice. We tried to stabilize the algorithm numerically. So in the discrete setting, you have a matrix that you're applying, which is no more a convolution matrix. We discover you can stabilize the algorithm by multiplying by its transpose. It works, but it's super slow, until we had the idea of resample iterative filtering. The idea is extremely simple, just 1 minute. What we have here is there's no more convolution. So the signal, the filter, which changes at every x position. So in practice, you have this filter and you adapt its support as the signal vary, okay? And you see, because the instantaneous frequency curve of your highest frequency IMF is like this, and your filter is basically following this curve, okay? That's adaptive local iterative filtering, ALIVE. What we realize is that this formula up there can be rewritten by change of variable. And you can make this function to be constant. And the signal, you need just to resample it. And so that's exactly what we do. So we take this signal, we resample in a way that this curve now becomes flat, horizontal. After the resampling, it's just flat. Stationary, now you can apply fast iterative filtering to extract using this bandwidth. You capture this component, you remove it, and then you sample back, okay? And that's the decomposition, right? You get, so that's the stationary component you extract, and this is like what it looks after the resampling back, okay? It's super fast, it's stable, robust, and plus allows us to prove a theorem, which tells us that ALIVE, the way we were implementing it, it could never work, okay, or better. You cannot guarantee the convergence, for sure. So we were trying really to discover something that we couldn't discover, okay? And this just thanks to this little twist in the problem. Here an example, so you take these 3 components, you add them together, the frequency, instantaneous frequency vary in this way. You can try with ALIVE, that's the error at each instant of time. Here you have computational time, the error in norm 2, and the number of iteration for each component. And you see with ALIVE, it takes 4 seconds and the error is pretty bad. With the resample iterative filtering, we take 1 second and the error is pretty low, as you see there. Here in the middle, you have the stable version of ALIVE, which takes almost 20 seconds to produce something which is, better, way better than ALIVE, but still not as good as resample iterative filtering. So we have it. And if you apply to real life signal, like the bat sound, we know that you have like instantaneous frequency curves like this. You can use these curves to extract the 3 components using resample iterative filtering. This is the decomposition if you just run fast iterative filtering. So you split it into pieces, right? And if you do instantaneous frequency curves of these 3 using IMFogram, those are the 3 curves you get. So it's a really neat and clean separation. Okay. So what is next? I mean, more mathematical analysis. We love to make analysis of everything, but there are questions that are unanswered, like how much the filter play a big role. Our understanding is not a big role, but we never dig a lot in that direction. The other big question is, what if your signal contains stochastic contribution? How much this method is going to, why the method is going to split in a certain way, or how much you can distinguish between stochastic and deterministic contribution. But more importantly, is this problem. So how to deal with intra-wave modulation in frequency, and how to separate components where they have an intra-wave modulation. Remember, IMFogram makes as an assumption that you don't have any intra-wave modulation. So inside each period, nothing changes. Okay, last year we had a conference in L'Aquila, my hometown, with a summer school and conference. Next year, we plan to replicate in Rome. And we're going to have a summer school with 3 courses. We will have Charles Chui from Stanford, Monica Dorfelder, and Andrea Morelli. And then following that, there will be a workshop on the topic. So we will talk about advanced techniques for signal processing. So you're all invited to participate. Okay, thanks a lot.
It's usually the way that we ask the present audience to ask any question if they have, and then proceed to online audience. So, anyone have any question?
Can you go through the intuition to the recycled alike?
Yeah. So you want me to go back to the slide?
Yes.
Yeah, sure. Which one? Let me go here, speaker. So this one here.
On the previous, you mentioned the intuition to this is something.
Okay, so the intuition is originally with the live, we were trying to, instead of fixing the filter here, the K or W filter, you are trying to adapt it point by point, because your signal may vary in frequency a lot, right? So instead of having, so you see here, that's the component you want to extract. Instead of using a fixed filter, which would be like a bandwidth, so it may capture just part of this curve, you want to have a filter which is adapting over time, so that the frequency you capture is changing over time, okay? And that's what you do with the live. So the filter is changing its shape, so the frequency you capture is changing. But that was not working. So then we had the idea to switch the problem. So if you do a change of variables here, instead of y, use g of z, okay? And g is just a resampling function. And you choose it in a way that kx g of z, it becomes a stationary function. So it's not changing anymore. So this filter now is basically a fixed filter. But the new signal is a resampled signal whose highest frequency component is now stationary. So it's just a resampling, right? Okay, that's the best thing. I mean, super simple, but it works. Yeah. So it's magic.
Anyone from the virtual audience had any question? Do you want to ask? You can unmute yourself. So we are thanking everybody for attending today's seminar, and thank you, Professor Antonio, for being here and present us with his recent research.